So this is a big theorem, the binomial theorem. The assumption here is n is a whole number, like 0, 1. Well, 0 is not very interesting. 1's not very interesting. So like 2, 3, 4, 5, 6, blah, blah, blah. The binomial theorem does work for non-whole numbers, but we don't present it at this level. You get it in Calc 2, perhaps. So the binomial theorem looks like this. Using that notation for the binomial coefficients, and an exponent of n, it turns out that a plus b to the n expands to be, well, the first binomial coefficient would be n choose 0, a to the n. And then the next term is going to be, well, if you write it in descending powers, the coefficient, of course, will be n choose 1. So this bottom number just goes up by 1 every time, and the top number stays at n. So that's easy enough to remember. And then the exponent on the a goes down by 1 in each term, right? If you write it in descending powers of n. A to the n minus 1. But then the exponent on the b, which starts at 0, so you don't see the b to the 0 here because that's just 1. The exponent on the b goes up by 1 every time. So it's n choose 1, a to the n minus 1, b to the 1. Okay, see if you see the pattern. What would the next one be? N choose 2, a to the n minus 2, b to the 2. Let's do one more. N choose 3, a to the n minus 3, b to the third. Now, it keeps going. Let me shrink this. Make some room. It keeps going, and I'll finish it off in a second, but I want to point something out. The exponent on the b matches the number that you're subtracting off the n for the exponent on the a. Did you notice that in each step? Works here as well, works here, and whoops, pointed at the wrong thing. And here. And that's exactly where that generic term came from a little bit ago. If you look at, say, the kth term, where k is between 0 and n, then the kth term would be, okay, by the way, also this bottom number matches the exponent on the n, right? On the b, rather, sorry. This bottom number here matches the exponent on the b. So those are some observations that are going to come in very, very handy. Okay, so let's look at what the kth term should look like. It would be n choose k times, okay, what would the exponent on the a be? N minus k. N minus whatever this number is right here. And then b to the k. So that's the pattern. And then eventually, I'm going to put another dot, dot, dot in there. So I'll shrink this down even more. And then eventually, what's going to happen though? Plus dot, dot, dot. Eventually, the counter number beneath the n is going to get up to n itself. N choose n, which means the exponent on the a is 0. N minus n, so you don't write it down. And the exponent on the b would be the n. And that's the binomial theorem. In this example, you're asked to find the fourth term in the expansion of x plus 2y to the 12th. So you're asked to find the literally the fourth term. So we're not saying n is equal to 4 here, so you got to be careful about that. Well, okay, what would the binomial coefficient be on the fourth term? So generically, n choose k. Well, n is always going to be this exponent up here on the binomial that you're expanding. So that part's easy. But if you start counting at 0, what's the k going to be for the fourth term? Not 4, 3. So that can be tricky. But then you just use this formula to get the variable part of it, right? So now that you've figured out what the k is, it's 3, not 4, you can just fill in for the a and the b. And then a is equal to x and b is equal to 2y. We'll fix that in a minute. So it would be a to the, what would it be? What would the exponent on the a be? Well, let's do the b first. What would the exponent on the b be? No, the b. If we do the b first, the exponent's always on the b is always that. It's the thing we call k. The exponent on the b is always the thing we call k. Oh, and my notation kind of stinks a little here because I'm putting in more than I was originally gonna. So putting in the full formula would be a to the n minus k, b to the k is what we said, right? So the exponent then, that's generic. And then for this particular expansion, the exponent on the b then would be 3, like you said. And what would the exponent on the a be? 12. You just have to subtract these two. That's kind of nice notation to remind you of that, right? 12 on the top, 3 on the bottom. Oh, the exponent on the a is just going to be that subtraction problem. If you think of it, it's not really a subtraction problem, but that's how we can align it vertically if you want to think of it that way. So 9. 12 minus 3. But wait, there's more. Because we think of a as x and 2y as b, so we got to fill that in. So fill that in, what do we get?
X to the 2y to the 12.
12 choose 3. I thought we said x to the 9th.
Oh, sorry.
X to the 9th. And then 2y, now the whole thing cubed, right? Would you guys buy that? Everybody okay with that? So what do you have to do when you're cubing the product 2 times y? You have to cube both the 2 and the y. So what does that give you? 8y cubed. Now, I don't really want to write down Pascal's triangle out to row 12, do you? I mean, you could. It wouldn't take that long. But I do want to show you how to do that on the calculator. On the calculator, the notation looks a little different. You're going to type in the 12 first, which makes sense. Go to the math menu, and then go over to PRB because this notation, what you're doing here, comes up a lot in probability, so PRB for probability. And you see the NCR? That's another notation that's used for n choose k, or the way your calculator denotes it is n choose r. So hit number 3 or go down to number 3 and hit enter. And then it was 12 choose 3, right? So you get 220. 220. So this 12 choose 3 is 220. But don't forget, we've got this 8 in here. And so you're going to have to take the 8 times the 220. What's 8 times 220?
1760.
1760, x to the 9th, y cubed.